Hi, I'm Chris, and in today's lesson we're going to be talking about KSP, or solubility product constant. So conceptually, KSP problems that you face in chemistry are going to work very similarly to what you may have already seen, hopefully have already seen, with equilibrium problems. If you haven't, feel free to check out some of the equilibrium problems that we cover here on our YouTube channel. But if you're already familiar with equilibrium, this is just the next step, and we're going to be talking about dissolving a solid in solution. So our solid here for this sample problem is aluminum hydroxide, AlOH3. And the reason that we have 3 OHs with 1 aluminum is because each hydroxide has a negative charge on it, so it takes 3 of those negative charges to balance out the +3 charge on aluminum. So when this dissociates in solution, when this breaks apart, you're going to get 1 Al3+ and then 3 OH minuses. And the coefficient here is going to be an important component in calculating our value for KSP. So the known value for KSP, which would be given to you in a problem, is 1.26 times 10 to the negative 33, and that's the KSP of aluminum hydroxide. Now when you see a problem like this on either a test that you might have in class or even a standardized test, depending on what you're preparing for, the question that would be asked about a problem like this is, what is the molar solubility? So here we're going to be asked for molar solubility, and molar solubility will, in this problem, be the value of x that we're going to solve for once we set up our KSP expression. So first let's take a look at this problem and see if we can set up a KSP expression. This will work very similarly to equilibrium, where you're going to have products over reactants, and the only thing that doesn't get included is pure solids or pure liquids. So in this case, because we're dissolving a solid in solution, we're really only going to write our KSP expression in terms of our products here. That's actually one area where KSP is a little bit easier than equilibrium, is you don't have to worry about what you have on that reactant side. So our KSP expression will simply be the concentration of our products, Al3+ and OH- times each other. Now we mentioned that this coefficient would come into play in this problem, and this is exactly where we're going to use it. So whatever your coefficient is on your product side for your KSP expression will act as an exponent on the concentration of that particular species. So here the hydroxide ion will have an exponent of 3, since in the reaction itself it has a coefficient of 3. So remember, coefficients get used as exponents when setting up your KSP expression. Now that we have that KSP expression, we need to try to plug in some values and solve. So if you're used to making an ice chart from your equilibrium problems, which is covered by a lot of chemistry teachers, stands for initial, change, and equilibrium. So you can still use an ice chart for a KSP expression, and here we're not concerned about any of the values for aluminum hydroxide itself, because remember, it's a solid, and if we look, we don't see the aluminum hydroxide as part of our KSP expression. So we only really are concerned with the values that we'll have for aluminum or for the hydroxide ion by themselves. So initially, for this particular problem, we don't have any aluminum or hydroxide already present in the solution. In certain cases you will, and that's referred to as common ion effect, which is covered in some of our later videos. But here, for aluminum and for hydroxide, we're starting with an initial concentration of 0. So the change is unknown, and that's what we're actually solving for. That's the molar solubility that the question is going to ask us to find. So the change here would be plus X amount. We don't really know what the amount is of aluminum that we're going to gain as the aluminum hydroxide dissolves. So we're going to call that X. Now again, this coefficient is going to come into play here, and we have to be careful. So when we take a look at this coefficient, we have a coefficient of 3, which means there are 3 times as many hydroxides as there are aluminum 3+ ions. So we have plus 3x in this column. And in your equilibrium line, you're just going to total everything up. 0 plus x is just x, and 0 plus 3x gives us 3x. So to solve this problem, we're going to go ahead and just plug in the value that we have in our equilibrium row for aluminum and for the OH-. So this would be x for aluminum and 3x for hydroxide, and it's still taken to the third power. And that's one thing sometimes students get stumped by. So just make sure that you keep in mind this coefficient is going to affect the value that you have here, and it's also going to impact the exponent that you have on your concentration value. So it's really like your coefficient gets used in those two places. So make sure that you don't only include the coefficient in one part of the problem, but it's actually going to affect the value that you have in the case of your molar solubility and the exponent of your KSP expression. And once we simplify this, a little math tip here, just keep in mind that whenever you have something in parentheses, if you take it to a certain exponent, that means every term in the parentheses must be taken to that exponent. So this will be 3 to the third and x to the third. And 3 to the third is 27. So this will simplify to x times 27x to the third. And when we multiply by x, if they have the same base, then you add those exponents. So we get 27x to the fourth is equal to our KSP value. And here we can just plug this in, 1.26 times 10 to the negative 33. And from there, there's a little bit of math required to solve. You can use a calculator, but here we would divide by 27 on both sides, and then we would take the fourth root of that result. And to save us a little bit of time here, since that's something that you can work out on your own, either by writing it out or using a calculator, we would get x equals 2.6 times 10 to the negative 9. So hopefully we now have a pretty good understanding of what to do with KSP problems that give us the KSP and ask for the molar solubility. If a question were to give you the molar solubility and ask for KSP, the setup will be exactly the same as what we see here. The only change that you'd need to make in that situation is you'd be plugging in your value of molar solubility for x, and you'd be solving for your value of KSP. So we would just flip-flop here, plugging in the value for x, and then solving for that KSP value. If you have further questions, please feel free to visit our website, sandersontestprep.com. The link is in the description below. Thanks for watching.